right? ETAP is the world's most comprehensive design and analysis tool for electrical power systems. And one of the modules under the ETAP software that we're going to be talking about today is switching sequence management, or SSM. This module can be added to your license just like you have, for example, load flow analysis, just like you have an arc flash module or a protection coordination star module, right? You do not need a third-party software. This is nested inside of your ETAP software. So what we're going to do is let's go ahead and get started with introducing the module, what it does, how you can use it to validate your normal operating switching sequences, for example. Along with switching sequence manager, what everyone also is maybe not aware of, there is a intelligent logic interlock, or the interlock enforcer, and we're going to be talking about that today also because they kind of go hand in hand, right? And we'll talk about what the differences are between the two, the interlock enforcer and the switching sequence manager, and how they could be used in your license. So who can benefit from using the intelligent switching sequence management module? Industries ranging from transmission, generation, distribution, very important industrial applications. In fact, the exercise that we're going to be going over today deals with an industrial site project, also offshore commercial users that have the need for validating their switching sequence procedures, right? It could be used on systems that are single phase, and obviously most importantly three-phase systems. There are many applications for SSM module, but predicting the results of executing a sequence is probably the most important one, right? Also identifying any switching errors that may result in unexpected consequence, right? That's why it is always so important to, before the operator is given a switching procedure, that it has been tested, that it has been verified, validated by the engineer. And the SSM module is the tool that in essence helps the electrical engineer validate, test, and verify that these switching sequences that are given to the operator will work or behave as expected, right? When performing scheduled outages and restoration sequences, right? Feeder balancing and load transfer. It's also used to check perhaps existing switching sequence procedure and trying to figure out or reduce cost and losses. So it is also a tool that can be used to verify any existing switching procedure that you may have already in place. Perhaps your switching procedure hasn't been verified and validated in many years. Perhaps your system has changed and you're constantly trying to keep up and validate with all these switching sequences. The switching sequence manager, SSM in ETAP, is the tool that was designed just for that. Okay, so also when you are on the power design phase, right? Front-end design or feed, and perhaps your client, your end user, is requesting a set of basic switching procedures. SSM is a tool for that as well. For double checking existing sequence procedures, for design and planning, as well as daily day-to-day operation of your network. So why choose ETAP? What are the advantages of using the ETAP switching sequence manager? And perhaps the most important and top reason is because the SSM module is an integrated part of ETAP. It's validated, just like all of our other nuclear high impact modules like arc flash, load flow, and short circuit, and there is no need really to purchase a third-party software. It's all enclosed in the ETAP suite, which means that when you purchase a copy of ETAP and you add your switching sequence manager, you can use the same electrical network or the one-line diagram that you build or that somebody has created already for your facility. The same one-line diagram, the same project, ETAP project that you've been using for arc flash, perhaps that it's being used for short circuit and load flow, right, to do the planning and the design, can also be used to perform the switching sequence validation, right? The other main advantage on why use ETAP for your switching sequence validation is because it can easily be integrated with the ETAP real-time solution. So what that means is if your electrical model is complete, updated, and it's being fed information from the field, such as meter information, real reactive power, voltage, the status on your main tie and breakers, right? All of that information can be imported, right, as an ETAP real-time configuration, and your switching sequence can be validated in real time before the operator actually performs the sequence. So it's like a third or a triple check, right? You typically design your switching sequence, you test it using various methods, one of them being the ETAP SSM module. You perhaps hand it over to the operator, but with ETAP real time you have that extra layer of protection where you design your switching sequence, you test it in SSM, or perhaps you test it by hand using hand calculations. Then you hand it over to the operator. Then ETAP real time sits like an HMI on your operator's room. You could think of it as a smart HMI, where before the operator actually follows a procedure, a switching procedure, they would just select it from the ETAP real-time HMI, and based on your existing system conditions, ETAP will give the operator feedback on what would happen if that sequence was executed in this point in time. So that's you could think of it as a third layer of protection. And the third reason we're going to talk about is it works with a built-in device interlock. So every copy of ETAP has the built-in device interlock, switching interlock enforcer feature that we're going to be talking about next. Okay. So the first thing we're going to do is let's talk about time-saving features. And by time-saving features, we're going to start talking about switching interlock enforcer, or SIE. And what the built-in switching interlock enforcer is a comprehensive interlock logic specified right at the switching device. So at this point, I'm going to actually switch over to my copy of ETAP so I can explain better what the built-in switching interlock enforcer is. So this is not yet the switching sequence manager module. We're going to introduce first the built-in switching interlock enforcer. Okay, so what I have here is an industrial system, and the interlock enforcer is built into everyone's ETAP copy. You could call upon it simply by double-clicking on any protected device or switching device. So if you double-click on any circuit breaker, for example, and you go over to Interlock, you could see under the Interlock tab the pre-switching logic and the post-switching logic. The way that pre-switching logic can be used is, for example, if we wanted to do work at this main incoming bus, right? We first may want to check that it is de-energized. One of the things that you could perform that operation, right, to make sure that bus is de-energized is by running a load flow analysis, for example. Let's just assume that this is the normal operating condition for this facility. So you've got your main incoming voltage is 13.8 kV. It is stepped down to 4160, and then you have down here most of your loads, which are 480 volts. We've got some large medium voltage motors and on the 4160 buses. And one of the things that I'm going to do using the ETAP's built-in interlock enforcer is I'm going to build some logic inside of this switch. This ground switch here is sensing basically is connected to the main incoming bus. So before we actually close this ground switch, before this incoming bus is grounded, we want to make sure that it's de-energized by opening this main CB10 circuit breaker, this CB19 circuit breaker feeding T transformer 2, and also this CB18 circuit breaker. So to do so, first thing you want to do is open the protected device, or in this case the switching device, like the ground switch. I will go over to the Interlock tab. Here's the Interlock tab. And I'm going to, under pre-switching logic, I'm going to select my action of close, meaning check the following pre-switching logic before closing the ground. And what we're going to do here is going to check that those three breakers, CB10, 19, and 18, here's CB10, equals open, and right, we got three. This should be and that my high voltage, medium voltage breakers CB19 is also open, and that CB18 over on the right hand side is also open. Okay, so The built-in pre-switch interlock enforcer is going to check the following three circuit breakers are actually in fact open before that ground switch is closed. ETAP automatically checks your logic. In fact, you could see it down below here on this window. There's a small preview that says pre-switch interlock logic action close if circuit breaker 10 is open, circuit breaker 19 is open, and circuit breaker 18 is open. So all those three conditions have to be met, otherwise we will get an error message. Click OK. Okay, so that's part one on using the ETAP's built-in interlock enforcer, setting up the logic, which we have already defined. Part number two is to actually enable the switching interlock enforcer. So right next to the option that is called check circuit continuity, there is a switching interlock enforcer logo. It's a little button just under your help pull down menu. You want to click on switch interlock enforcer. That becomes enable, which means that now, right, you could actually right click on your ground switch and you could click where it says grounded, right? And then ETAP is preventing me from grounding that switch, and the reason why is because the conditions inside the interlock have not been met, right? So ETAP is actually preventing the user, or in this case the operator, from closing in on an energized bus. So here's, in order to close that switch, we need to open CB10, right? We need to open CB19. We need to open CB18. Now my main incoming bus is de-energized. Remember, the switching interlock enforcer is still enabled. So now what I'll do is I'll ground it, and now the error message is no longer shown. Okay, so everyone that has an ETAP copy already has this capability built in on their licenses. So this is a module that everyone listening to this presentation already has on their modules. Okay, again, this system, right, or this particular feature can be used as you're validating switching sequences. Okay, so what I'm going to do now is I'm going to restore. So now main incoming is isolated. If I was to run a load flow analysis, you could see, right, that all of my loads are being fed locally from the generator. Okay. So what I'm going to do now is I'll go ahead and open this ground and then restore my system back to normal. Okay, so I'm going to open. So again, we're back in the normal operating condition, right? So now, in order, this is where the switching sequence manager comes in. Now there is a way to automate that task that we just performed by hand using the interlock enforcer. We can now, on the study toolbar, head over to the switching sequence management module. Here's the switching sequence management. You notice that my one-line diagram goes from like an operator's screen or HMI to more of a design tool, because that's exactly what switching sequence manager is. It's really a tool to help you test, design switching sequences, as well as analyzing. So every time in ETAP, for the most part, when you're performing analysis, right, you would typically have your white background and the elements are black, right? And whenever you bring your system in real time, or you're looking at operating, right, existing operating conditions, you will have the more common, right, operators feel and look like an HMI, just like the way I had it earlier. So let's go over to Switching Sequence Manager now, and let's automate that task. Let's automate that very simple switching sequence that we just performed, checking that before the ground switch is closed, right, to check that the bus is safe to work on, is de-energized, that those circuit breakers are open. They're isolating main incoming bus. So to perform that simulation inside the Switching Sequence Manager, what we're going to do is we're going to create a new switching sequence. So this is the switching sequence editor, and one of the things that I wanted to introduce at this point is that the switching sequence, and this is also part of the features of the SSM module, right, is that you can actually create these switching sequences right from the one-line diagram. So you can actually graphically add actions to the switching sequence editor, right, verify them visually, and then step through the switching sequence procedure. Okay, so now that we have the analysis view in the background, right, we got our one-line diagram, what we're going to do is graphically step through the simulation. So we're going to before we check that the main incoming is grounded, or check the voltage or closed in the ground switch, we want to make sure that CB10 is open, CB19 is open, CB18 is open. That effectively isolates your main incoming bus. And the last step is to ground it, right? There it is. So that's our switching sequence procedure. I'm going to click OK. I've called it check point of common coupling 1, check PCC 1. So what I'll do is, you notice there's a pull down menu in the switching sequence manager module that would have all of your switching procedures. So right now I only have one called check point of common coupling 1. Okay, and but you may have many different switching sequences right under this pull down menu. You set them up ahead of time, and before the operator actually performs any switching events, they would simply select that switching procedure from the drop-down list and then run it as follows. So over on the right-hand side, I'm going to click on Run Switching Sequence. Okay, here is my sequence viewer. I haven't actually started the simulation. Okay, so the first thing that we're given is the steady state operation of the system. So how the system is operating right at this point. So let me just go ahead and display the units for everyone. Okay, so we're looking at kVA, right, power flow in the system. So this is what the steady state condition of the system is. So what we're going to do is we're now going to step through this switching sequence. So I'm going to click on Start, and the results below, so the results that you see here are basically alerts. They're giving us information such as under voltage, right? If you notice that one of the conditions here is called under voltage, that just simply means that that particular bus, it's experiencing a voltage drop that is greater than the alert threshold. So right now I have my alert threshold set to 3%. So any voltage drop, any buses that experience a voltage drop greater than 3% will be listed under these alerts right here. It also checks for cables that may be overloaded. It also checks for circuit breakers that may be overloaded. Basically what it does is it checks the power flow going through your branch or your protected device as you're stepping through the sequence, and it gives you in real time the alerts, right, the results on what under voltage or overload conditions you may see. For protected devices, what the module will do is it'll check the power flow going through the frame and compare it against the protected device frame size. For the cables, similar. It'll check, say, cable and transformers. It'll check the power flow going through the branch, in this case, whether it's transformer or cable, and check it against the transformer rating or your cable allowed ampacity. Okay, so what I've done here is I completed just one action. I open the main circuit breaker, CV10. This is the main incoming 13.8 kV circuit breaker. I'm going to step through the second action, which is open CV19. I'm going to step through the next action, open CV18. So now my main incoming is completely isolated. My system is now running fully on a generator, right? And then I'm going to execute the very last step, which is close of that grounding switch. As you could see, there were no errors that came up because none of the logic, the interlock logic inside the grounded switch was violated. I am, however, getting some pretty large under voltage, so pretty large voltage drops. I'm also getting some overload conditions, right, on some of my main feeders. Cable 2, one of my transformers is overloaded. Also, my generator, right, my local generator is overloaded. It is a 10 megawatt rated synchronous generator that is operating at 11.3. So all of these alerts are graphically shown both on the one-line diagram, right, as well as on this switching sequence view alert viewer. So then you're then free to use all of these results to come up with perhaps the best switching sequence. In this case, right, if I wanted to go on completely local generation, perhaps one of the things that I would have to include here after closing in the ground switch to make sure that it's de-energized is perhaps do some load shedding, right? So perhaps open some of the breakers for the non-essential loads so that my system doesn't go into a critical or unstable condition. Because at this point, the generator is definitely overloaded. The system would probably not be able to recover if the main 13.8 kV bus was isolated. Also, right, cable 2 and T3 are overloaded. Okay, so let's now do a let's also talk about how the switching sequence manager, right, is part of the ETAP real-time solution. So just as I showed in the brief example that I went over, is I had to enter all of this information by hand, which is typically okay for when you're doing design, right? You're 2 or 3 years away from actually commissioning the facility, so you're doing design preliminary calculations. You're perhaps verifying your main switching procedures, and that's okay to enter all of that information by hand. However, once your system has been commissioned, the design phase is over, you could now take your one-line diagram, right, connect it to your ETAP real-time module and have it populate right, real-time data from your existing meters. Also, ETAP will sense the position on your main tie breakers, your generator breaker, um, uh, utility tie, main breakers, so that you don't have to have, right? In that case, what happens is you wouldn't have to have all of your switching sequences predefined ahead of time. You could actually consider cases, right, that perhaps are not even specified on the procedures. So what the operator would do in the if your system is connected to ETAP real-time data, is they can actually, before performing any kind of switching procedure, they would just get the existing real-time data. ETAP will then automatically, right, set the initial condition on all your protected devices. Basically, your steady-state load flow, as we see it here, would automatically come from the field, right? That's your initial condition. And then the operator, right, could then very simply, right, check that, for example, before performing or closing in that ground, they would perform the simulation in ETAP, and ETAP will automatically give the operator any alerts or any warning. In this case, the grounding switch is closed on a hot or energized element before actually performing, right, the actual switching procedure. So you could think of the ETAP real time, right, as a way for the operators to perform switching sequence procedures that may not be part of the overall procedure. Perhaps for a given disturbance in the system, there is no switching sequence provided in the handbook, so you or the operator, the electrical engineer or the operator, can simply use the ETAP impedance-based one-line diagram and the real-time data to do a quick on-the-fly what if, right, check to make sure that if a particular switching sequence is performed, that it won't have a negative impact or it won't affect the stability of the system. Okay, so the ETAP real time is part of the intelligent substation solution. Again, it allows the dispatcher to build a complete switching program using a graphical user interface and execute the switching plan all in one step. Okay, so what I'll do is I'm going to go over one last example where we transfer the load through a tie breaker. Okay, remember, before any switching sequence is executed, ETAP, right, verifies whether the sequence is compliant with the safety switching procedures that you, by verifying whether the sequence is compliant, meaning the logic that you enter into the switching element or the tie, in this case could be a protected device, right, a tie breaker, and it requests confirmation during the execution of each step. Basically, as you step through the steps, you could see, right, any undervoltage or overload condition before actually placing the switching sequence into operation. Okay, so let's do the following example. Oops, I've got to open this ground. Okay, so what we're gonna do on this example is, so we've got just a small industrial site, and what we're going to do is we're actually going to check the condition. So the operator is given the task to do or the engineer has done the task to check that in the event that one of these transformers, let's say in this case T5, so this branch right here that I'm highlighting in red, so the branch on the left, is out of service. Perhaps the transformer needs to be undergo maintenance. Perhaps there's a problem with T5. So the facility, right, or the entire load, all of these low voltage or 480 volt loads need to be shifted through the other transformer, in this case T4. So one of the things you could perform is, let's go over to Switching Sequence Manager, right? We're going to create a brand new switching sequence order, and we're going to call this load shift. Load shift. Okay, and the first thing that we're going to do for performing load shift is we're going to close a tie. So we're going to close CB4. Give me 1 second. So what happens is, based on the existing condition, the tie is in fact closed. So I need to open it before. Okay, gotta open this. So here is a main tie main configuration. So you've got basically a system on the left, another system on the right, and for redundancy, right, we have the tie. In this case, there's a medium voltage tie called CB3 and a low voltage tie called CB4. Okay, so this is our day-to-day operating condition, or let's just call it normal condition. So let's go back to Switching Sequence Manager, and I had started, right, a new, we're gonna call this switching sequence load shift. Okay, and for load shift, what we're gonna do is first we're going to, in order to isolate the branch transformer 5 that's over on the left hand side, is we're gonna open CB22 on the primary side of, or on the line side of cable 5, and CB9, which is on the secondary side of T5. And before we isolate that transformer, we're going to shift the load through this low voltage tie called CB4. So that's action number 1. As you could see, very easy graphically. All you have to do is tap on the protected device. So we're just closing the tie. Now we're going to isolate the branch where transformer 5 is. So I'm going to click on CB9, and that sets it, that isolates it. Right, CB22 open. So the branch is completely isolated. You could see here that the branch is now grayed out. It is completely de-energized. And now what we're going to do is to check for any perhaps large voltage drops or overload conditions, right? We're going to run this simulation called load shift, this switching procedure. So let's go ahead and run switching sequence. Okay, and the first thing that you see is your steady state condition, meaning how the system is operating, right, under the normal configuration. So you could see how both ties, the low voltage tie CB4 is open. Should be, yep, it's open. It's right here, and also CB3 is open. And what we're going to do is we're going to step through the switching sequence. So the first thing we're going to do is click on step start. So that first condition, now we're closing the main CB4 tie. Next step is to begin to isolate the transformer. Transformer is completely isolated. So I've stepped through all 3 actions. And now, right, for our results, we just expand the window here, the alert view, and we can focus on anything that perhaps may have a voltage drop that is greater than 5% or 3%. The user can specify these values inside the briefcase, the study case. But most importantly, right, we need to pay attention to any possible overloads. So we have an overload on cable 7. We have an overload on a circuit breaker, right, CB8, which is, I believe is, yep, right here. You notice that graphically, ETAP will highlight any critical alerts shown on the results. So you could see how CB8 right here, it is, perhaps I could use right here, so that I just grabbed it onto a better cursor. So you could see that the alerts report on the right hand side correlate with any element that is highlighted in red. So there's an overload problem with CB8, cable 7, which it's highlighted on the report right here. It's also experiencing overload condition. T4 is not overloaded, so that's why it doesn't appear here. And also there is an overload on the generator. So it says that the generator is overloaded. Okay, so let me go back here to finish off with the presentation. As you can see, the substation automation feature, right, allows the local operator, right, to take into account any switching sequences that may not have been tested ahead of time. Perhaps they haven't been defined, right? And it gives local alerts to make sure that there's no problems. What I'm going to do here is I'm going to quickly go over